Okay, so we're getting into chapter 3, which is our third module here. This is all about the electronic structure of the atom. And with this electronic structure of the atom, what we are going to be looking at in this unit is we're going to be taking that idea of the atom that we constructed last chapter, the Rutherford model of the atom, nucleus in the middle, electrons flying around it, and we're going to modify it and adapt it based upon some technological advances of the early 20th century that led us to a deeper and better understanding of the atom itself. So overall, there's a lot in this particular module. And for today, we're going to focus on primarily these first 3 ideas. Talking primarily about the electromagnetic spectrum, light, frequency, wave theory, kind of some classical mechanics kind of stuff. And at the very, very end of today, we'll start to look into some of the challenges of classical physics, which will lead us into Friday's lecture, where we get into more of the challenges and how the technology of the time ended up leading us to what is called the quantum mechanical model of the atom, which we'll then explore much more deeply next week when we talk about quantum numbers, we talk about electron configurations, and we talk about periodic trends. So those are the 5 kind of ideas that we're breaking this unit into. Waves for today, classical issues and the Bohr model Friday, quantum numbers on Monday, electron configurations next Wednesday, and periodic trends next Friday. So let's kind of start here with where we are and where we were. At the end of module 2, going back to last Friday, last Wednesday, we had the gold foil experiment. We had the nuclear model of the atom. The whole idea, remember the gold foil experiment proving that there was a nucleus. We shoot those alpha particles at that gold foil, and the majority of them go straight through. The reason they go straight through is because all that they encountered were electrons, if anything. But when they hit something, they tended to hit it pretty hard and deflected pretty greatly as a result. That let us know that there was a big, compact, dense nucleus in the middle of that atom. And later experiments proved that that nucleus had positive particles and that nucleus had neutral particles, the protons and the neutrons. Now, the Rutherford model ended at the idea that these electrons were just kind of circling around that nucleus. And if you remember the picture of that model of the atom, it looked something like this, where I've got my nucleus in the middle, and I've got these orbiting electrons kind of going all around it. This picture of the atom, the Rutherfordian model, is something that even today we still recognize as, oh yeah, that's what an atom looks like. Or at least that's what we are told an atom looks like based on some pictures in popular media. But the problem with this picture is that it does represent an unrealistic kind of situation. I've got these negative particles, right? They're going around this big positive center. Why doesn't the attraction between positive and negative eventually cause that electron to slowly work its way into the nucleus itself? They're attracted to each other, right? Why does that electron stay at a fixed distance? Can't really explain that with the Rutherford model. In fact, a lot of the questions that we started to ask couldn't be explained by classical physics at all. And so what needed to be done was we needed to have a new model come forth. Now, no model can come forth, no theory can be destroyed unless we've got good evidence to do so. And right around the brink of the 20th century, there was a large technological boom that took place that really improved our instrumentation, that really improved our ability to measure things. And this also led to a lot of discoveries and a lot of very interesting kinds of conclusions as a result. We already saw some of that. Thomson's electrode cathode ray experiment, proving that there were negatively charged particles in everything. We call those electrons. Millikan's oil drop experiment, where we were able to isolate the individual charge on that electron. The gold foil experiment, and later work of Chadwick and others to actually prove that there were protons and neutrons in that nucleus. Those all came about because there were things being discovered that hadn't been discovered before, one of them being radiation. And when we start to explain some of these things, the world of Isaac Newton, dating back to the 1700s and 1800s, didn't fit so well anymore. So quantum mechanics was a way to seek out that change that was necessary. Now, to get a handle on quantum mechanics, which I will warn you, quantum mechanics can get very, very deep, very, very quickly. We're going to try our best to stay in the shallow end as long as possible. But if it's something that kind of piques your interest, you can go way off into the deep end of quantum mechanics pretty quickly. Quantum mechanics, though, needs to start with an idea of wave theory. Wave theory starts with electromagnetic radiation. Electromagnetic radiation is a concept here that talks about things that are energetic being composed of waves. So electric fields, magnetic fields, these are composed of waves. Light, sound, these are composed of waves. And when it comes to waves, we can characterize waves by three things. The wavelength, which is abbreviated with the lowercase Greek letter lambda. The frequency, which is characterized by the lowercase Greek letter nu. So that is a Greek letter nu, not the letter V. V in the world of physics is velocity or speed. And amplitude, which does not have an abbreviation. We'll talk about that in a minute. So most things that are energetic in some kind of way, so not matter, but energy, can focus itself in terms of this wave theory. And of these things, the most relevant of those to us is the idea of light. Light is a form of electromagnetic radiation. We'll talk about a broad kind of scope of electromagnetic radiation later on here. But we have three main dominant characteristics. Amplitude. Amplitude refers to the intensity of light. So when we talk about amplitude, we are usually talking about brightness or dimness of light. If we're talking about other kinds of waves, sound waves, we could talk about amplitude in terms of decibel level. So the amplitude of a wave of a very loud sound would be very large, but a quiet sound would be very small. We can also talk about things in terms of wavelength. Wavelength is the measurement of a wave from tip to tip or from bottom to bottom. So if we go to this previous picture here, we can measure the wavelength of this particular wave by looking at its distance between one wave crest and another, or one wave trough and another. And those distances would be the same regardless of measurement there. Frequency, on the other hand, which is measured in hertz. Hertz are reciprocal seconds. There is an inverse relationship between wavelength and frequency. So frequency, you can kind of think about, if I'm standing here at this fixed point and I'm looking at this wave as it is going by, frequency would be the number of complete wavelengths I see in a given second. Now, since we're talking about light, and light travels at the speed of light, 2.998 times 10 to the 8th meters per second, I know that regardless of what my frequency is, or my wavelength rather, I'm going to see a lot of waves in that second. Because in this nearly 300 million meters, even if I have a wavelength that is really, really long, I'm still going to see several of them in that second, because 300 million meters are going by every second. So frequency for us, one thing that we're going to have to kind of come to grips with frequency, is that frequency is always going to be a large value. Usually frequency is going to be expressed in scientific notation because the frequency value is going to be just that large. Wavelengths are usually measured in meters or nanometers. It really just depends upon what it is that we're looking at. Most visible light is measured in nanometers. And remember that nanometers are 10 to the negative 9th per meters. The inverse relationship of wavelength and frequency is notable here. Because all light is traveling at the exact same speed, we're going to have a definitive relationship between wavelength and frequency. The longer the wavelength is, the smaller the frequency is going to be. Because since they're all traveling at the same rate, I'm looking at how many waves I'm going to see crossing by. The longer the wave is, the fewer waves I'm going to see. By contrast, if I have a short wavelength, that means the frequency is going to be that much higher. Because again, more waves going by, I'm going to see more of them in that given second. because they're shorter. We can relate the two concepts using this equation. This is called the speed of light equation. And the speed of light equation is wavelength in meters multiplied by frequency in hertz gives us the speed of light. And we can rearrange this accordingly to whatever scenario or situation that we need. So, since the speed of light is a constant, pretty rare that we're going to need to calculate it. Chances are good we're going to use one of these other two equations. If I need the frequency, I take the speed of light and I divide it by the wavelength. If I need the wavelength, I take the speed of light and I divide it by the frequency. And again, just to illustrate that difference, that relationship between wavelength and frequency, if we can imagine that this is the moment that we are peaking at the wave, and this represents an equal amount of time, wave A represents two complete wavelengths. We're starting at the tip of one wave up to the first and up to the second. So two wavelengths in total for wave A. For B, we've got 1, we've got 2, we've got 3, we've got 4 complete wavelengths in B. So the frequency of B is literally double that of A, and that's because it is half of the wavelength. So there's a nice definitive linear relationship between the two, but they are inversely related. One goes up, the other one goes down. So let's do a practice problem with this calculation. Just to get used to using these equations. What is the frequency of light associated with a wavelength of 640 nanometers? So our speed of light equation says that C is equal to the lambda times nu, wavelength times frequency. We're going to want to rearrange that since we're trying to find frequency. So frequency is the speed of light divided by the wavelength. Now, the speed of light is a constant, 2.998 times 10 to the 8th meters per second. The wavelength here, we are given 640 nanometers. Now, before we plug this into our calculator, one thing that we absolutely need to recognize is that these two units don't match up. On one hand, I've got meters. On the other, I've got nanometers. Meters and nanometers are not the same unit. They're the same kind of measurement. They're both measurements of distance, but they're not the same unit. I need to convert one into the other to get it to work out. Now, here's where our knowledge of the metric system can come in handy. I know that nanometers are 10 to the negative 9th in terms of meters. So I'm going to rewrite this value here as 640 times 10 to the negative 9th meters. Is this improper scientific notation? Absolutely. Will my calculator be able to tell the difference? You betcha. So if I want to put this properly into scientific notation, I'd have to move this decimal point over 2 spots. And so that would mean I'd have to reduce this number by 2. So it'd be 10 to the negative 7th instead of 10 to the negative 9th. But again, my calculator won't know the difference. So if I'm just trying to kind of save myself a little bit of time here, improper scientific notation is okay right here. I'm just putting it into the calculator. I'll make it proper by the time I report the actual answer. So 2.998 times 10 to the 8th, divided by 640 times 10 to the negative 9th. And the two significant figures, again, I can only use 2 because this 0 here is not significant. I get 4.7 times 10 to the 14th hertz. Which would be the same thing as 4.7 times 10 to the 14th reciprocal seconds. So 1 over S and hertz are the same thing. And the reason we get 1 over S here is because if I cancel out my meters, all that's left is S in the denominator and nothing in the numerator. And so that nothing isn't 0 because that would mean that the unit is 0. If everything cancels out, then the unit is 1. But 1 over seconds and hertz are the same thing. All right, any questions with this practice problem? Pretty straightforward equation using here. All right. Go ahead and try this one on your own then. What is the frequency in hertz of an electromagnetic wave with a wavelength of 457 nanometers? All right, let's see how we did. Now, walking around, most of you were on the right track. If you got the wrong answer, it was usually one of two things. First thing, scientific notation, if you're not putting it into the calculator properly, if you're still putting in scientific notation as whatever number times 10 caret, whatever the exponent is, you have to be really careful about that because your calculator, without fail, will follow the order of operations. And so if you tell it to divide by 457 and then multiply by 10 to the negative 9th, it's going to treat those as two separate things. Now, if you use the scientific notation button on your calculator, it should treat it as one separate thing because it really is one separate thing. So make sure that if you don't know how to access scientific notation on your calculator, come talk to me. I'll tell you how to do it. And the second thing is if you don't use that, make sure you use parentheses around the scientific notation pieces so that when you're dividing by the whole number and not just the first part of the scientific notation. So if you got something here that was like 10 to the negative second, 10 to the negative third, that was the mistake. Otherwise, should have been pretty much exactly like the first example. Any questions for me before we move on to the next thing? So we're moving on from just looking at light. And we're talking about a broader spectrum of energy waves known as the electromagnetic spectrum. Now, in the electromagnetic spectrum, we have a variety of different kinds of radiation that are present. And the thing about these radiation types is that you'll notice that they range in very differing amounts of energy and differing amounts of seriousness. So on this spectrum, we start with radio waves. Radio waves are present right now in this room. There are radio waves traveling through your body right now. And it's not just because we're only a couple of blocks away from a radio transmitter over there at the business building. They're low frequency. They're high wavelength. They're not terribly energetic. And that's why they can pass through you and you wouldn't even know that they're there. As we go down the scale here, we're going to see that a couple of things are happening. First of all, we are getting more energetic. And we're getting more energetic because we're getting shorter in wavelength and longer in frequency. And we'll talk more about that on Friday, but there is definitely a relationship that's starting to build. So from radio waves, we go to microwaves. From microwaves, we go to IR, infrared radiation. We feel infrared radiation primarily as heat. We go to the visible part of the spectrum, the part of the spectrum that we can actually see and actually pick out individual colors from. Beyond that is the ultraviolet light. This is the light that is slightly more energetic than violet light. So Roy G. Biv represents the colors of light in their order of energy, red light being the least energetic, violet light being the most energetic. Ultraviolet light is beyond that violet light in terms of its energy. We see it in sunlight, we see it in UV lamps. We know that we know what a sunburn can do to our bodies. That's primarily caused by the interactions of UV light in our skin. And then on the far end of the scale, short wavelength, high frequency light. X-rays, gamma rays, these are used in medical imaging. This is the stuff that's found in outer space and in nuclear events. High energy, also high damage if we're not wearing the proper equipment. Which is why when you have an X-ray taken, they cover your vital organs in some sort of a lead shield to prevent those rays from penetrating into your body and messing up your organs. The electromagnetic spectrum is just that. It is a continuous march of frequency and wavelength from that low energy, high wavelength to this high frequency stuff on the other side with gamma rays. Inside of the visible spectrum, you can see that this is truly a spectrum. It is a continuous blur of color from red at the low energy side to violet at the high energy side. The electromagnetic spectrum is a continuous spectrum. One frequency blends right into the next and into the next and into the next. So with that in mind, let's go ahead and rank these out from longest wavelength at the top to shortest wavelength at the bottom. All right, so if we start to look at this, right away, we see X-rays. We know that X-rays are high energy, low frequency, or high energy, low wavelength, high frequency light. They're going to be the shortest here on the bottom. From here, just have to kind of know our order. So infrared light is actually the first one on the list here. And the reason it's the first one on the list is because infrared light, infrared literally means that it is, if red is the least energetic form of visible light, infrared is just that much less energetic. So it is just on that side of visible light, which is why we can feel it as heat, but we really can't see it very well at all. From there, we need to move into the visible part of the spectrum. So we've done this one and we've done this one. We can make a similar kind of argument for UV light. UV light is just on the other side of the visible spectrum. So since green light and orange light are both in the visible, UV light would be just slightly shorter than those. So now it's a matter of orange versus green. Remember your order. It's Roy G. Biv. Red, orange, yellow, green. So orange is going to be less energetic, higher wavelength than green is. And so there would be the proper order. Infrared, then orange, then green, then UV, then your X-rays. So the last thing that we want to talk about today, and we're really just going to focus on this first bullet point here out of section 4, the emission spectroscopy, here are some experiments, some observations that were being able to be made in the early part of the 20th century that did not match what we knew about classical wave theory. So we've talked about light this far. It's continuous. It has a wavelength and a frequency that are directly related to each other, but inverse. What we're going to see in these experiments here in the early part of the 20th century is we're going to find each one of them has some kind of defining characteristic that goes against what we think we know about light. So we're going to start with emission spectroscopy. And you're going to get a really good opportunity next week to do emission spectroscopy, to do these kinds of experiments in your lab and see it firsthand for yourself. But the idea is this. You know, most of you have done this at some point in time. If you hold up a prism to light, you'll notice that that prism bends the light and I get a continuous rainbow. That's just a furtherance of what we already know about light theory and waves from what we've already talked about. But that's with white light. White light bends and we get the visible spectrum. Well, what if instead of white light, we took a sample of a gas, shocked it to no end with electricity, got all of the electrons inside of that gas super excited, so that they're jumping all over the place, and then we held up that prism to it. Well, the result of that experiment is not a continuous band of light. The result of that experiment instead is these. They're called emission spectrum. And these emission spectra are very unique because each element has its own unique emission spectrum, almost like a fingerprint that helps to tell us what that thing is. And the other thing that's really weird about these lines are always in the same exact place, same exact energy, same exact wavelength, always. Now that doesn't make sense in terms of wave theory. Wave theory would tell us, okay, well, if I have light going through this gas sample, it's just going to behave like anything else. Light should pass through, should get a prism. That's not what happens here. We'll tackle this a little bit on Friday, but the idea here comes down to what we are going to call energy levels. Specific places, specific amounts of energy that an electron can hold inside of an atom. And these lines that we see are related to movement from one energy level to another. Now, for hydrogen, because hydrogen's the easiest to kind of pinpoint because hydrogen only has one electron to worry about, these spectra were given specific names. The Lyman series, the Balmer series, the Paschen series. And what they correlate to is a specific set of transitions that end at a particular energy level. So the Lyman series all end at the first energy level. The Balmer series, which give us the visible lines that we can see, all end at the second energy level. The Paschen series all end at the third energy level. They're all higher wavelength. They end up being in the infrared region. But we can quantify any transition that occurs using this equation. This is called the Rydberg equation. Rydberg equation equates wavelength as 1 over lambda related to R. R is what's called the Rydberg constant, 1.097 times 10 to the 7th reciprocal meters. And these values of N, NF, and NI, they relate to the energy levels that the atom, that the electron starts at and ends at. So NF would refer to the final energy level where the electron ends. And I would refer to the initial energy level, the place where the electron begins. And that's where we're stopping for today. So as you find your way to the exit here, make sure that you get in that last question before you go. And then you're going to see all of this stuff again in that assignment 3-1 that's due tomorrow night. Have a great afternoon. I'll see you on Friday.